our YouTube channel St. Wilfred College of Arts, Commerce and Science. Myself Asmita Agaj, faculty of St. Wilfred College. Today's my lecture is about crown ethers, mycelids and cryptands. In that, we are going to see about first crown ethers, about their structures, about their synthesis. After that, we are going to see about nomenclatures and their applications. After that, cryptand. In cryptand, we are going to see about their definition, their synthesis, and their applications. Last one is the mycelids. In mycelids, we are going to see about formation of mycelids, definition of mycelids, synthesis of mycelids, reactions of mycelids, and last one, its application. Okay, so let's start with crown ethers. Crown ethers, these are nothing but the family of a cyclic polyether. The crown ethers are a cyclic chemical compound that consists of a ring containing several ether groups. After that, these are the large ring compounds containing several oxygen atoms in regular pattern. If you are able to see, then the structure shows that the oxygens are separated by two carbon atoms. There is ether linkage present and it is on one cyclic compound. After that, the most crown ethers are oligomers of ethylene oxide. The important member of this series are tetramer, that is N is equal to 4, the pentamer, N is equal to 5, and hexamer, N is equal to 6. The term crown refers to resemblance between the structure crown ether bound to a cation and a crown sitting on person's head. After that, crown ethers are widely used as a phase transfer catalyst and are able to transport ionic compound into organic phase. Means ionic phase compound is transported or can do reactions in organic phase. After that, next one is the nomenclature. The crown ethers are designated as per their IUPAC nomenclature and also by their short names. It is also represented by notations. Crown ether are named as X crown Y, where X is nothing but the total number of atoms in ring and Y is total number of oxygen. If you see this structure, in this structure, total number of atoms are 18 and after that we are adding name crown and 6 is nothing but the number of oxygen atom present in that compound. So the final name of this compound will be 18 crown 6. After that, the first number designated the ring size and the second number designate the number of oxygen atom in the ring. In places of oxygen, other heteroatom we can use like sulfur. After that, nitrogen also use. After that, if sulfur is present as a heteroatom, then that crown ether will called as a thiac crown ether. If that heteroatom is a nitrogen, then this is called as a Agaj crown ether. There are two structures. First one is of a thiac crown ether, which contains sulfur as a heteroatom, and second one is of a Agaj crown ether, which contains nitrogen as a heteroatom. After that, the relationship between the crown ether and ion, that is called as a host-guest interaction. Where crown ether act as a host while the coordinating metal act as a guest. Example, dibenzo 18C6. C means crown, K plus complex. This special feature of crown ethers are as a phase transfer catalyst. Due to formation of a complex through metal ion, crown ether act as a very powerful phase transfer catalyst. After that, they are used to transfer ionic compound into organic phase from aqueous phase. Hence, they are called as a ionophores. After that, unlike quaternary ammonium salt, crown ether are neutral molecule and the cation is held together by ion dipole bond instead of a strong covalent bond. Hence, crown ether are better phase transfer catalyst as compared to quaternary ammonium salt. After that, Crown ethers forms a stable complex with most of the time potassium and sodium ions. These complexes is then stabilized by ion dipole forces between the cation. 6 oxygen atom of polyethylene, also called as a crown ether. The cation is then fits comfortably within the cavity of crown ether. Lipophilicity of the external of the crown ether makes them soluble in organic solvent of very low polarity. When it passes through organic phase from aqueous phase, it carries anion with it. The negative charge of an anion is shielded from the charge of a central cation atom by bulky crown ether linkage. Thus, due to loose bonding between cation and anion, outermost anion is easily available for reaction. After that, we will move forward with applications of crown ether, where we can use that crown ether. First, it is used in photocyanation reaction. Next one, in resolution of a racemic mixture. After that, in benzoin condensation rearrangement reaction. After that, heterocyclization. Next, synthesis of furanons. And next one is the acetylation of a secondary amine in presence of a primary amine. These are the application where we can use crown ether as a phase transfer catalyst. These all are the reaction where we are using crown ether as a catalyst. Okay, next one is the reaction. Esterification reaction of a crown ether. Crown ether have been used for esterification. Esterification means addition of a ester group. Ester group will be there in a product. Let's see, para-bromophenol. This one is our first reactant, which name is a para-bromophenol ester, have been prepared by the reactions of a para-bromophenol bromide. Okay, with potassium salt of a carboxylic acid using 18 crown C as the solubilizing agent, which yield 92% of phenacetyl ester of a fatty acid, which we are going to obtain. So our reactant is para-bromophenol bromide. Okay. After that, we are going to react it with the carboxylic acid and nothing but an salt, potassium salt of carboxylic acid. We are going to use crown ether, which is 18 crown 6. Okay. And finally, we will get our product, which is para-bromophenol ester. If you are able to see, then what happens? That Br will be removed, bromine atom, which is a halogen atom, it is removed, and addition of a RCO2 group, means ester group is take place on this carbon atom, where and finally we will get our product as para-bromophenol ester. Only Br is removed, bromine atom is removed. After that, next one is our cryptands. Cryptands, these are the family of synthetic bicyclic compounds and polycyclic multidentate ligand for a variety of cations. After that, cryptands are nothing but an macrocyclic amino ethers. Cryptand are synthesized and investigated by Professor Len in 1971 to 1975. After that, cryptand have high ability to form complexes, preferentially with alkaline earth metal and transition metal ions. The term cryptand implies that these ligands bind substrate in crypts, entering the guest as in a burial. After that, this molecule are a three-dimensional analog of a crown ethers, but are more selective and strong as a complexes for the guest ion. After that, these resulting complexes are a lipophilic compounds. After that, synthetic applications for cryptands. These are esterification. We can use that cryptand in esterification reaction. After that, saponification reaction, anhydride formation reaction, potassium permanganate oxidation. The reaction in which we are using potassium permanganate for oxidation purpose. We are going to use cryptand also there. After that, in aromatic substitution reaction, we are going to use it. After that, in elimination reaction, we are going to use cryptand. After that, in displacement reaction, we are using cryptand as a catalyst. Next one is generation of a carbon formation reactions. We are going to use it. After that, superoxide ions and alkylation reaction, in which oxygen alkylation, carbon alkylation and alkylation. This type of reaction can take place in presence of a cryptand. After that, analytical application. First, determination of a gold in geological sample. We can use that as a catalyst for this type of reaction. After that, supercritical full extraction of a trace metal from solid and liquid materials. After that, in ionic liquid in analytical chemistry. After that, oxidation reaction, as we said, as we are going to use it with the help of with KMNO4. After that, we can use it to determine aldehydes. After that, crown ethers are mostly used in laboratory as a phase transfer catalyst. It transfer compound from ionic to organic phase. After that, next topic is our mycelials. Mycelials, this is an aggregate of monomer surfactant molecule dispersed in a liquid colloid. They are formed in aqueous solution by quaternary ammonium salt or carboxylate salt, which contain long chain of an atom. These molecules are ionic in nature and also called as a surfactant. It contains one head, that is hydrophilic region, which is in contact with the surrounding solvent, and sequenting the hydrophobic tail, which in which region in the mycelial center, also called as oil in water mycelium. Next one, inverse mycelium have the head group at the center with the tail extending out. At low concentration, the surfactant molecule are soluble in water. But if their concentration is inert, the surfactant molecule begin to come closer and closer to each other to form a aggregate molecule. At a certain specific concentration, large aggregate molecule are formed, and these molecule are called as a mycelium. Next one, the concentration at which formation of a mycelium is complete is called as a critical mycelium concentration. One aggregate mycelium molecule contains most of the time 15 to 150 mycelium of a surfactant. Mycelium formation leads to a sudden change in physical property of a solvent, such as surface conductivity, melting, and boiling points. Each molecule of surfactant has a one hydrophobic tail and hydrophilic head. After that, how are the mycelium formed? Okay, as we said, when the concentration of surfactant reaches to the critical concentration level, the hydrophobe of a surfactant will organize to form a mycelium. The mycelium, the lipophilic hydrocarbon chains are oriented toward the interior of mycelium, leaving the hydrophilic group on contact with aqueous medium. After that, as we said, critical mycelium concentration is nothing but the concentration at which mycelium formation become appreciable. Okay, or we can say that it started aggregated. After that, mycelium formation, if you are able to see, there is one diagram which show how that mycelium is going to form. If you are going to see, these are the this one is the one mycelium, in which this one is your head, which is hydrophilic, and tail is hydrophobic. Okay, when amphipathic molecules are dispersed in water, mycelium are formed above certain critical concentration known as a CMC. After that, a high CMC causes rapid exchange of constitution component, fast disintegration upon dilution, and less stability. The molecule will rearrange themselves to form a mycelium. This one is the mycelium structure. As our concentration reach toward the CMC, that all mycelium form this type of aggregate compound, which is known as a mycelium. After that, this one is the structure of mycelium, in which these are the hydrophilic heads from the surface of the mycelium, which are in contact with our solvents. After that, the inner part, it is nothing but your hydrophobic tails, and it is composed at the interior of a mycelium. After that, next one is the applications of mycelium, where we are going to use that mycelium. First one, conication mixed mycelium are produced from two molecules, lecithin and glycogenic. After that, it is used in treatment of vitamin K. If your vitamin K deficiency is there, then we are going to use mycelium. After that, deficiency, bleeding DAB in neonates and infants. After that, last one is a conclusion. Reverse mycelia are relatively simple but are valuable tool for the study of various aspects of a life science. We are going to use that myceles most of the time in life science reaction. After that, reverse myceles are controlled by variation factors like detergent type, detergent concentration, water content, hydration ratio, organic solvent, etc. By manipulating this variable of the system, we can explore enzyme and protein chemistry in better way and gain useful information about the processes which are going to take place in the physiological system. After that, reverse mycelia also act as a nano reactor to perform many unconventional reaction like a esterification, separation of valuable and biodegradation of a hydrophobic pollutants. Thank you.